Welcome to Phase 2. Until now the solver itself has been a black box, you pressed run and trusted it. This series doesn't allow black boxes. So let's open the most important one. OpenFOAM solves steady incompressible flow, and it's built on an algorithm called simple. Almost everyone treats it as magic. By the end of this episode, you'll know exactly what it does and why it has to. Incompressible flow comes down to two equations. Keep your eye on what each one gives us. The momentum equation gives us velocity, but notice, it needs the pressure gradient on the right-hand side to do so. The continuity equation says mass is conserved, the velocity field must be divergence-free. But look closely, pressure doesn't even appear in it. Hold that thought. Here's the trap at the heart of incompressible CFD. Line them up and count. Velocity has a home, the momentum equation solves for it. Good. But pressure has no equation of its own. Momentum uses pressure, continuity ignores it. There is literally no formula that says pressure equals. It's a chicken and egg trap. Momentum needs pressure to find velocity, but nothing hands us pressure. This single gap is the reason incompressible solvers exist at all. Simple is how we escape it. Simple's insight is beautiful. If continuity won't give us a pressure equation directly, we'll force it to indirectly. Start by guessing pressure. Any reasonable guess. Plug that guess into momentum and solve for a velocity. Call it U star. Here's the key. Because our pressure was only a guess, this velocity won't conserve mass. It violates continuity, and the size of that violation is information. We feed that continuity error into a new equation, derived by combining momentum and continuity, that tells us exactly how to adjust the pressure to reduce it. That is our manufactured pressure equation. We correct both pressure and velocity, and repeat. Each pass, the continuity error shrinks until the fields are consistent. Drawn as a cycle, the whole algorithm looks like this, and this picture is worth memorizing. 1. The momentum predictor gives a first velocity from the current pressure. 2. The pressure equation produces a correction from the continuity error. 3. We apply that correction to both pressure and velocity, so mass is now conserved. 4. Check the residuals. Not converged? Go round again. Predict, correct, check, repeat. Every outer iteration you saw scrolling in the log back in episode 6 is exactly one trip around this loop. Two last pieces. First, the name. The S in simple stands for semi-implicit because we don't solve momentum and pressure together in one giant system. We solve them in turn, passing corrections back and forth. That's what makes it tractable. But solving them separately has a cost, each correction can overshoot. Left unchecked, pressure and velocity swing back and forth and the whole thing can diverge. So we under-relax, we only apply a fraction of each correction, maybe 70% of the pressure update, 30% of the momentum. It's slower per step, but it converges instead of exploding. This is why steady runs need relaxation factors. With the algorithm in hand, two things in fvSolution suddenly read as plain English. The simple dictionary sets the convergence targets, the residual levels that end the loop. And relaxation factors are exactly the under-relaxation we just talked about, fixed pressure at 0.3, momentum at 0.7. If a steady run diverges, these relaxation factors are the first dial you lower. Now you know why they exist, they tame the guess and correct swing. That's simple. There's no direct pressure equation, so the algorithm manufactures one from the continuity error, then loops, predict, correct, check under-relaxing to stay stable. Not magic. Just a clever escape from a chicken and egg problem. Simple finds the steady, final state. But most real flows change in time, they shed vortices, they pulse. Next episode, OpenFOAM, and how the same pressure-velocity idea is adapted to march through time. See you there. Welcome to phase